So when we think about light as coming through, we're going to talk about a little bit of math, and we're just going to start by assuming that our polarizer axis aligns with the y-axis for the sake of the math. And here we're going to assume that we have one definition of which way our electric field is going. So we're not quite going to do this calculation initially for unpolarized light. We're going to do it for polarized light in some direction. So it comes through and there's some angle theta that our initial light makes with our polarization, our polarizer axis. We can imagine breaking this into a component that is perpendicular to the axis and parallel to the axis. Now, the component that is perpendicular to the axis is basically in our x direction. The component that's parallel to our axis is in our y direction. But then instead of thinking about it as perpendicular and parallel, we can convert it into the initial amplitude that it had, and then sine and cosine of that angle that it's making. So this is just trig. Now the ideal polarizer actually only transmits the parallel component. So the parallel component was in J, that's this, and so this is basically blocked. It doesn't go anywhere. So what this means is that your transmitted light perfectly aligns with your polarizer axis, but we've again lost some of our intensity. So this is fundamentally how we imagine this working. So our intensity is proportional to our electric field squared. And if you remember back to when we defined intensity for electromagnetic waves, there were some coefficients out front, but it's proportional to electric field squared. So our transmitted intensity is going to be equal to our initial intensity, assuming that our initial intensity is polarized. And this is important and something I will come back to later. Polarized. It's a little bit different if initially we have unpolarized light. But then we have cosine squared, and the reason it's squared now is because we've taken how our electric field has changed and squared that. And that is going to be now the angle between our polarizer axis and whatever our initial polarization was. So when you see something like this, that is implying that our initial light was polarized. So our intensity only ever decreases, it can't get bigger, and it has some new orientation. Note that this orientation aligns with the axis of the polarizer. In the book, it always uses these kind of little sticking out pieces to denote the axis of the polarizer. If I hand you a polarizer in class, you will have to figure out the polarization axis one way or another. Depending on what polarizer you're handed, there are different ways to figure that out. So most of the time we don't actually use the electric field magnitude itself. We usually do use intensity. And the reason for that is intensity is what we actually observe. We would observe intensity with our eyes. We would observe intensity with a detector. We don't usually directly measure the electric field magnitude, at least in visible light. So that's why we're working with intensity. So this is MALUS's law, and that's just this equation. So it's a law in that he figured out it was true all the time. It's not necessarily something as fundamental as many of the electromagnetic rules that we've met. So this isn't fundamental physics, but it's something that always happens. So what's a little more interesting is when we're dealing with two polarizers. And in this scenario, which doesn't have to be the scenario you always have, our initial light is unpolarized. So and we can use different notations to think about this. If we initially have I0 and then we come here to I1, we can ask, how has this changed? Now, it would be a mistake to try to use cosine squared of theta because initially our light was unpolarized. Effectively what you do is do kind of an integral over all of the possible angles, but you can kind of say on average it's a 45-degree angle, and so your intensity after passing unpolarized light through is actually I0 over 2. So that's something to just kind of to know. Then we pass our light through and get our second intensity, and now I2 is going to be equal to I1 times our cosine squared theta, where theta was the angle. Notice that the second one is up and this one is theta, right? There's an angle theta here. So if you want to relate your final intensity to your initial intensity, it would be I naught over 2 cosine squared theta. Now I can keep adding more and more polarizers, and in each case all you have to do is pass on the intensity that you had to the next one, and this theta is always the angle between subsequent, so consecutive polarizers. So we could have 4 or 5 polarizers in a row, and you would just be calculating this step by step. Don't try to take any shortcuts. If you try to take shortcuts with these, you will probably just flat out be wrong. And do make sure you understand if your initial light has a polarization or whether your initial light is unpolarized. Frequently what we do is we don't actually worry about what our initial intensity is, and we might in fact just call this I naught at this step after we have some polarization, and then call this I1. So frequently we call the first polarizer literally the polarizer, meaning it's creating polarized light, and the second one the analyzer, which is the one that then does some math for us or figures out what the polarization is. I don't fully understand why that's the choice of words here. But do make sure you understand if we're starting with unpolarized light or not, and if you're told what the intensity is, whether it was this unpolarized light or after it has been polarized. So to think a little bit about what's happening, if we have a standard thing such as the light bouncing off this paper, this here would be unpolarized. So in this situation, notice this red line. This is telling you the axis of polarization. So when we look at this, this looks to be about 50% as bright as the unpolarized one was. And that makes sense. If this is unpolarized and it's going through a polarizer, you get 50% of your intensity. But then we pass it through a second polarizer, which is the same direction. Compare this area to this area. That really looks the same. Why would these be equal? Well, this angle here, because they're aligned, theta equals 0. Cosine squared of 0 equals 1. So notice that all three of these brightnesses really look the same because this is passed through one, and passing light that's polarized through a polarizer that's perfectly aligned doesn't diminish the intensity. Here we see that we have a certain amount of light there. In each case, again, it would be about 50% of our intensity. But now this looks a little dimmer. And what would this intensity be? Well, here we would now have cosine squared of 45 degrees. And that then tells us how our intensity has decreased going from here to there. Now lastly, we have 90 degrees. Cosine squared of 90 degrees is 0. And if you look here, what does that intensity look like? Well, that intensity looks like 0. So when you have polarizers that are perpendicular to one another, they block all of the light coming through. To do some really quick practice, let's look at these two scenarios here. And the question is, if we have initially unpolarized light, what is our final intensity? So if we have some initial intensity here, we know that in the middle we now have I naught over 2. Why? Because if it was initially unpolarized, once we pass it through a polarizer, we get I naught over 2. Now we need to figure out what theta is. Be careful here because theta needs to be the angle between the polarizers. What is this? Theta equals 90 degrees. So don't just take the angle with respect to vertical, make sure that you're thinking about the angle between your polarizers. So in this case, theta is equal to 90, so our final intensity is 0. We have blocked all of the light. Now in the second situation, I again have I naught. I pass it through a polarizer. Again, our initial intensity was unpolarized, and so we have I naught over 2. Now we again look at theta, and we notice, oh, this is 30 degrees from vertical. This is 30 degrees from vertical in the same direction. That's kind of important. So theta here equals 0. So our final intensity in this situation is just I naught over 2. We don't have our full intensity, but that's simply because we've lost some intensity going from unpolarized light to polarized light. So I hope that this is kind of a concrete example for how to think about some more complicated situations, at least with two polarizers where initially you have unpolarized light.